All right, so this week is a bit of a heavier, I don't know if heavy is the right word. Technical, yeah. We're talking about information and specifically DNA and like how that comes about. So it's an interesting topic. I guess maybe we can start on like, what do you guys know about information, DNA, how it works? What are your impressions of it coming into us somewhat blind?
Simple. It's 4 things.
Yep.
Super easy.
What 4 things?
Adenosine, taurine, sita something, and guanine.
At Grundy Center. That's how my middle school.
At Grundy Center.
Grundy Center. That's how we remembered it.
Yeah.
At Grundy Center.
Yeah.
At Grundy Center.
I went to school at Grundy Center. So the teacher's like, at Grundy Center, never forget. Never forgot.
There you go.
There you go. You'll never forget.
Grundy Center.
Grundy Center.
So what was that again? Can you say that one? What makes up DNA?
So it's ATGC and
Adenosine, thymine, guanine, silane. Right?
So
Okay.
yep. Those are 3
4.
nucleic acids is what they are. And they make up the bonds inside the double helix. So A and C and T bind, I think, and then
A and C and G.
A and
A
C.
and T, G and Z.
Yeah.
At Grundy Center.
Yep. So like they always bind with their partner nucleic acid, nucleic base, I think, nucleotide.
Because of their shape, is that right? Like the way each one is shaped.
Yeah.
That's how they connect. If
Yep.
I remember.
Like they fit like puzzle pieces.
Yeah. Like one is, I mean, if you go cartoon style, I suppose, like one's rounded and then one like kind of goes in like this, and then one is like pointed, and then it has a side that's more like it'll connect. If that's actually legit, that was middle school. It was a long time ago.
Yeah, they're definitely, so like chemically the bonds only work in certain directions, and they form the genetic code, which is, a lot of these pairs of information. So there's obvious implications there, like that it's equated to programming, right? Like Bill Gates has said that it's like, DNA is the most sophisticated form of like programming language that we've seen. It's often Francis Collin, he was the head of the World Health Organization. He was part of the Human Genome Project that mapped the whole genome of a human. He's actually a Christian, but he wrote a book called The Language of God, which he talks about like how DNA and that information is it's hard to explain those things. Like how did that information get there? There's no known process or explanation for why these chemicals, one, came to form DNA, and then how, even if like there is infinitely more ways to combine these things that are just random noise. So like how did that information get there? Like that's the heart of the question, or the heart of the problem. And the secular scientists have various explanations for it, one of which we'll talk about a little bit more detail, which is the RNA World Hypothesis. But let's back up a little bit. So DNA, we've also heard of like a gene. Does anyone like know what a gene is, or the definition of a gene? I mean, we all hear that word, right? Gene is like, but like what do we mean when we say gene?
Did genes go with chromosomes? I mean, do they put those two together?
Yeah. I mean, chromosomes contain genes.
Okay.
Yeah. But basically, a gene is a unit of heredity, typically understood as a section of DNA that contains the instructions for a particular protein. So it's basically, if DNA is a cookbook, a gene is a recipe for a specific protein in most cases. So you got the whole DNA strand, which has all of these recipes in it for these various proteins. And those are used to form the proteins, which then create the molecular machines that run our cells and all of that kind of stuff we talked about last week. Yeah,
I know.
last month.
Okay.
Yeah, so that's what a gene is. It's just that chunk that describes a protein. You can also think of like, there's another analogy in here where like a hard drive is equated to a DNA molecule. The software is the genetic information. That's the ATGC information or the code. And then the hardware is the molecular machines that then execute the building of these proteins. So that's another analogy. There's a lot of analogies out there, like the chef cookbook recipe is one that you come across quite a bit. Like if you were to Google it on YouTube. So the genome, as I said, that there's the genome project. The genome is just the full complement of genetic information that an organism has. There's also something that you might not have heard of. That's a little bit more in the weeds, but there's something called a codon. Codon. So that is it's basically just 3 letters. It's the 3 letters. It's like ATG or CAA. And what those codons do is they represent a nucleotide base, or adenine, cytosine, thymine, guanine. Like the codon codes for one of those
Pairs?
One of those nucleic bases.
So 1 of 4.
No, sorry, that's wrong.
Okay.
A codon codes for amino acids, like the building blocks of proteins.
Okay.
So like, it's basically like if you think of the amino acids as Legos, every 3 letters in the DNA says use this Lego piece. And then there are mechanisms. So there's mechanisms called transcription and translation in DNA. And these mechanisms basically read the DNA, read these codons, and those codons tell the responsible nanomachine, which would be there's a couple involved in the process, but basically it's like, we need this piece to form, this is the next piece we need to build this protein. And it's an amino acid. And it's like, okay, so you got a bunch of these, they can be like hundreds of codons long, and you build these proteins.
So is it like a computer within a computer? Instructions within instructions?
I'm not sure what you mean by that.
Because I'm not really sure what you mean by codon either.
Okay,
Even
yeah.
though I'm listening,
So
I don't.
it's
I understand what you're saying.
Okay.
Yeah. Yeah, and I'm not an expert in this.
No, I know,
so
but
at the basic level, a codon is just 3 letters that represent. So in your DNA, as you read the
But
strand.
hang on a second.
Yeah.
So like we just talked about the 4, like the ATGC.
Yeah.
Okay. Is a codon related to those?
Yes. So the codon. So if you read out DNA, right? If you just are like looking at DNA and you got an A, you got a T, you got a G, you got a C, you got an A, you got a C, like you're reading that out as you're going down this one side of the strand. Every
You're
3.
talking about a double helix strand.
Yes. As you're going through DNA, you're reading it out. Every 3 letters is a group.
Okay.
So ATG, that's a group.
Okay.
And that is called a codon.
Okay.
And that codes for a specific building block for a protein.
Okay.
So it's saying, ATG, I need some specific building block. And then CAC, that's a different building block. And so it's the code that represents what is needed to build a specific protein.
I know you're not an expert in it, but why is it 3 and not 4? If there's 4 letters, why is it codons are only 3?
That's a good question. I don't know if there's really an answer to that.
No problem.
It's likely to do with the fact that the number of potential amino acids, like 3, like the variations with 4 letters. You can also think of codons as words.
Sure.
Like, so you have 4 letters and you have 3-letter words. All of those combinations represent the total number of like amino acids. Well, like that combination matches.
Okay.
Right. So there's like,
it's a hard concept to like really comprehend. You're doing a good job. It's just a lot to
it
understand.
is.
Would it be the same as why you don't use 26 letters in every single word?
Yeah, kind of.
You
Yeah.
only need certain
a good
letters for
example.
certain words.
And even why we have 26 letters in the alphabet is because of like the phonetic sounds we can make with our mouth. You know, the 26 letters kind of just represent that in English well. So, yeah. But I mean, some of that answer is like,
That's why it's wild.
it
and
just is.
interesting.
There's also aspects of codons because like there are, so I mentioned ATG as a codon. I'm pretty sure that's the one that, yeah, it's the start signal in the DNA. So you think about it, like how do you know, like you have a really long piece of DNA with all of these letters, how do you know where to start to code for a protein? Well, it's often the specific combination ATG. So ATG is like a codon that represents the start signal. So it's like start the protein here, and then there's also a end signal, which is often TGA. So you have ATG to start it, then you have all of these building blocks you need, and then you have an end. So like that would be a protein. And so as this protein gets built, there are mechanisms that get these pieces and put them together to build the protein. Yeah, it's a complex process. And I think the interesting thing is, I mean, there's a lot of interesting things, but like a Darwinistic new atheism, they would put, so like how evolution is supposed to work is you have random changes in this code, right? So, you know, those can happen by just chance, like a cosmic ray comes in, hits the DNA, knocks a C to a T in the sequence. And that is going to change the structure of the protein that is resulting. Like just a single letter change is going to say, okay, it was a start signal, now it's something else. And now you've just merged two together. Or like a small change can be a big difference. Like if you think of like a sentence and you knock out a letter and switch it with a different letter, what are the chances that that forms a real word? And like that seems more harmful than helpful. Like what are the chances that you randomly start changing letters in the book Moby Dick and then you get a different story out of it?
That's how we get cancer.
Yeah, in a lot of ways.
Mutations, yeah.
Yeah, mutations are almost always harmful. But, you know, Darwinistic approach would say that, you know, sometimes they are beneficial and those beneficial ones get kept. And then like the non-beneficial ones, you know, if they're really harmful, they just makes the organism die so it can't reproduce. And so that doesn't live on. But the ones that, you know, help, like claws, like Wolverine claws or whatever, you know, those those can get stuck around because they benefit survival is the theory, really. But you can see how this is like problematic. Like
There's also the article that literally came out and said that that's not actually true. That study that just came out.
Yeah, I mean, there was a headline this week on a study that was done that was trying to track the evolution changes in a specific species of lizard. And
No, not in a specific species, but just in lizards on this chunk of land.
Yeah. So they like captured a bunch of these lizards, they tagged them all, and like every 6 months they would catch them. And then they would make all these measurements and they would say, oh, you know, this one had longer, stronger legs. And they would track all of this over time through multiple years. And basically all the changes they saw, like they expected to say, oh, the lizards that had stronger, faster legs would live longer. Like that was the hypothesis and they would reproduce. And then like the population would start moving that direction. That's evolution. The theory. They're still lizards, but even in that study, for the length they did it, all the changes they saw, like the minor fluctuations in the species, they all pretty much washed each other out long term. Like, you know, there was a year where long leg lizards was more prevalent, and then the next year it was short-legged, and then but then if you average it all out, nothing really changed.
So survival of the fittest, they were finding that that's not really actually working. And what was interesting though is that's the first time that study was ever done, since Darwinism became the standard in how we came to be, how everything came to be. This guy that ran the study is how come this has never been tested? It's just been and he wasn't in it for creationism or anything. He's just how has this never been done before? So he's let's go. And it was a really interesting paper. They released it a couple days ago. So it's out there if you want to find it and read it. The end of the article is basically the guy goes, evolution is still happening, but we're not really sure how at the end. Okay. It's just not happening the way we assumed, I think is how he says it.
Yeah. So also with DNA, we have a bit of a chicken and egg problem with it, because if we rewind it back to origin of life sort of questions, what came first? Was it the DNA, or was it the proteins that are used to make DNA? Because all DNA is proteins. It's a specific sequence of specific proteins and the nucleotide bases. So how does that work? They are dependent on each other, just like a chicken and an egg are dependent on each other, and they cycle. How do you get that first? And then you also have the cell membranes, and all of these things are very dependent on one another, and you kind of need all of them to work. That's the idea of irreducible complexity. So you need DNA, you need these specific enzymes or proteins to help form DNA, and then you also need a cell membrane to protect it all. So the big theory that most scientists will go to explain, the best explanation for this currently scientifically is what they call the RNA World Hypothesis. And so let's first talk about what RNA is. So DNA is more popularized. RNA has specific roles, and there's specific variations of it. In the process of transcription, so what happens is the DNA gets unzipped, and a specialized nanomachine or protein, RNA polymerase, that's what it is. It comes in and it reads, it transcripts that DNA sequence into another strand that pairs with it, and that new strand is RNA. So it's basically, let's go back to the cookbook analogy. DNA is a cookbook. RNA would be the note card that you write down the recipe on and take it to the chef.
So if you didn't want to take the whole cookbook into the kitchen and open it up and be here's what you need to make, instead you would sit there and be I want this recipe. Now I can leave the cookbook that weighs 1,000 pounds here and just take the one recipe for the chef.
Yep. Okay. It's the instructions for a specific protein assembly, and that gets coded into an RNA. And then that RNA goes to a ribosome, and that gets read in the ribosome. And then another specialized kind of RNA, it's called a tRNA or a transfer RNA. It goes out and it picks up the building blocks or the Lego pieces out in the cell and brings them to the ribosome. And then there's a special key function. So for, let's say it's, building block A has a special shape here. And then the tRNA that's carrying the right piece matches up with that perfectly. And then it drops it off. And then the next codon's hey, we need X, Y, and Z piece. And then tRNA goes and picks that and drops that off. So it there's a lot of pieces going on, and RNA is a a big factor in that process, because it not only does it carry the messenger RNA or the mRNA, which has the instructions on it, the tRNA are what go and get it and bring the right pieces. And then it gets all assembled. This protein gets assembled in a ribosome.
So question, I know you're not an expert on this. You might not be able to answer it. I can look it up later if I need to. What's the point? Like if you have DNA, which has everything that you need, right? All of your building blocks, it's like the 1,000-pound cookbook, okay? What is the point of RNA breaking that down piece by piece? Is it an efficiency thing for the cell?
Yeah, presumably. And it's also like to protect the DNA, like I would think. I mean, I'm not sure exactly, right? Like there's probably a lot of reasons that it makes sense, but like, you know, you keep your main instructions separate, and then, you know, like the note card, it's okay. You know, it can go out and do what it's needed. It executes on it. So it's kind of like a separation of concerns. Like DNA is just to store it.
Yeah. And
then RNA is to like make use of it.
Okay.
Yeah. Yeah. So the RNA World Hypothesis says that things started more simply. So DNA was not around originally, like really early in life. This theory would say at first there was RNA. So RNA can self-replicate fairly easily in terms of chemistry. It's really not all that easy. Like it doesn't just happen naturally right now. Scientists kind of can coax it to do that, but it can. There's ways it can replicate, and so they're basically saying that RNA was the original thing, and it played multiple roles, like the transfer RNA and the messenger RNA, and maybe some other roles. It was like a primitive version, so everything just kind of worked off of RNA.
So simpler life forms, simpler breakdown of information, aka RNA.
Yeah, because I mean that's their big problem. Like this is a very complex orchestra of events that are happening inside of every cell in your body. Yeah. And how do you explain that? Well, it's very, very difficult. So it's like they need to simplify. Like if they can figure out a way it can work more simply and then get more advanced with little changes over time, that's easier to like. So it has to work that way. Like that's how evolution works. It has to start from simple to complex. And so they're trying to figure out like how can what seems like a very irreducibly complex system like DNA, transcription, translation, all the pieces seem very dependent on one another. Yeah. How can we think about a simpler way of doing it? And like this RNA world is like, maybe this could work.
Gotcha.
Like this could work. Like the RNA has the right characteristics. It has information in it. So that's the main explanatory factor. But there's a lot of holes in that theory, as you can imagine. Like the big one is it doesn't explain at all where the information came from still. Like RNA still needs that information of like, these are the instructions for a specific protein that is needed for some function. So like, yeah, it doesn't explain that big starting problem, initial problem.
So we know what happens if there's a mutation in DNA. Like you get a mutation, so you get a gene that does something it's probably wasn't designed initially to do. And it can cause cancer, it can cause growths, it can cause whatever. Or anyway, is this part of this discussion? Maybe you're not super aware of it, but what happens when is there a potential for mutation in RNA? Because I would assume that they would say, like, mutations is how we got started. Like, good mutations continue to happen, and, like, it was kept in survival of the fittest. Can you have mutations in RNA? Yeah. And if it's so simple, like, if something is that simple, quote, unquote, what happens when you get a mutation in a very simple thing? That would seem like it would 100% not work, or a higher likely that mutation would be detrimental to the organism.
Yeah. So. Yeah. There's Well, yeah, I think what you're hitting on some concept of like information theory in general,
Okay.
which would say that like English language has redundancies built into it because like communicating information has errors built in. Things get messed up. So like if you changed a letter in a sentence, you could probably still read that sentence.
Right.
You change a letter in a word, it depends on the word. If it was long enough, you probably could do it. But if it was like the word me and you changed E to A, you'd have to do some guessing. And so like, but if it was in a sentence, you could probably figure out, from the context of that sentence, I know that it should be me.
Yeah.
So with every information system, there's always redundancies built into it and context built into it for error correction.
Right.
DNA is no different. There is error correction built into it, which is an interesting area in itself. But
so there's a redundancy protocol in RNA potentially?
Probably, but like if it's shorter and more simplified, like that's harder to bring in that extra context to know what it should have been. Right? Like when you have a more succinct message that every piece of the, every letter matters. And if you change one, then the whole meaning is lost.
Right.
That doesn't leave room for error correction. Right. So like it's more likely that it's destructive.
And then do they just explain that away with like time? Like RNA would have mutations, but over billions or millions of years with the right blah, 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 you're going to get something that works and that's what's going to survive.
Yeah.
Okay.
Yeah.
When you said RNA can self-replicate, can DNA self-replicate?
It does it does. Yeah. That's one of the reasons it has the two strands, because it also unzips and then it can match. So like the fact that there's two strands is there's so many interesting things about DNA. The fact that there's two strands and like each pair can only be matched with its counterpart means that you can copy it, right? So you can have this side and then you can rebuild the left half, and this side you rebuild the right half, and now you have two strands and it has the same information. And so I don't know some of this stuff off the top of my head, but like DNA does replicate, and it's usually like cell divisions, right? So cells split and grow and divide. And every time they split, they have to copy that whole, like you need a new set of DNA for that new cell. So it has to replicate that way. Yep. Yeah. So RNA world that doesn't explain information. The other problem with RNA world is it doesn't solve the protein problem. So RNA can fill some interesting roles, like the tRNA and the messenger RNA, but it doesn't replace proteins. Like proteins are the structural machines that do the work. So in the DNA transcription and translation process, there's multiple proteins at work doing things, reading the DNA, copying it, getting the right things and bringing it in. There's no explanation for like how RNA could fill some of those roles. Additionally, so I guess it's kind of off in the first one, but let's read this real quick. Yeah, like the first self-replicating RNA molecule, there's still no explanation on how that formed other than chance. And RNA, you're still talking about like RNA being like 250 nucleotides long. So the ATG, like the code, 250 long. And the chances of those all lining up just right is, a big number. It says in here 1 to 10 to the 150th, which is a huge, huge number. And, we hit this concept before, but that's a lot of complex specified information to get just right. Yeah. So like RNA World is an interesting theory, and it kind of gives a plausible yet very generic explanation on like it could have been something like this, but like there's no proof of it. Like they've done some studies in the lab where they can get RNA to replicate, but there's no natural mechanisms that have been observed to my knowledge to say, yeah, this is like a confirmed theory. It's kind of like the multiverse theory in that way, where it's like, here's a way it could have happened, but we don't have a lot of the specifics. Like we don't know exactly how it happened, but you know, it's in the realm of possibility that these broad things could have happened. You know, and they would argue, not necessarily wrongly, that you know that's how theories start, and then you start figuring out the specifics. But you know, there's big holes in it, so it's hard to say that this is a sure thing.
But isn't that also like when you get down, like we talked about this, I think the last time we met was the headlines. That's like, we've created this in the lab, or we've been able to replicate this or this in laboratory situations. If and when, if they haven't already, like you can get DNA to replicate. I mean, like that's how crimes get solved. Like you get a little bit, and you can like create the whole chain and be like, now we know who this belongs to. Okay, anyway, but when it comes down to it, proving that it just happened on its own, like the proteins were just there, or they figured themselves out. Is that the big jump? Like when we listen to James Stewart.
Yeah.
Is that where the big jump is? Where the, like, is it the amino acids? Is it the proteins? What is it where they're like, there's just no possible way, even in the next 1,000 years, will we ever come to a place where, is it the amino acids or the proteins are just coming together on their own and kickstarting the process with no human interaction whatsoever? Which one of those is it?
Well, I mean, one is a cascade of really hard problems. So, like, step one is you need amino acids, and you need the right ones.
Okay.
That's where last week we talked about the Miller-Urey experiment. Mm-hmm. That experiment showed that they were able to, in the lab with arguably somewhat realistic conditions on early Earth, which we've now said is probably not true, they were able to form some amino acids using electricity and certain chemicals. So like they got like the raw Lego pieces of those amino acids. But, you know, to do that in a way that's actually useful, you know, not as much, because you need a lot of them, and you need them to stay there.
Right, they have to sustain themselves and continue moving forward without just dissolving. Yeah,
because like there's a lot of chemical volatility. Like just because you can make a chemical doesn't mean it's going to stay that way for very long. You know, these amino acids, I think James Stewart said something like, you know, they can last from hours to maybe days, but you need a lot to last a while, because then like, so now you have all the, you know, let's say you have some of the Lego pieces you need, and then you need them to all come together in a way that's useful, right? So like you could take a box of Legos and shake it all day long and not get a house out of it. Mm-hmm. Like that's kind of the problem. That's the next problem. It's like, okay, now even let's say you have those amino acids, you have all of the ones you need, you know, they got to put themselves together in a way that's useful. And not only useful, but you have to then say that house out of that, you know, tub of Lego block. Let's say you happen to get that house to be built. Mm-hmm. You got to do that again. Like it has to replicate. Mm-hmm. It has to have some kind of process to keep it going, and to then have a process to make it improve. Mm-hmm. And so like there's these, you know, and that's even more simplified than it is. Like almost each step, there's a big gulf of unknowns, and like we just don't know how it happened. And the biggest of them all is the information problem, because information doesn't just happen, you know, like it's the whole like monkeys writing Mozart
Shakespeare.
or Shakespeare, or whatever it is. Yeah. It just doesn't happen in any realistic time frame. And so how do you, and like, you need that to happen so many times. Like there has to be that's why the intelligent design theory is so attractive to me, is it's just like, how else do you do it? And so like Stephen Meyer, the head of the Discovery Institute, like information is his big, I think, one of the best arguments for intelligent design. And it comes down to this, like, what explanatory factor do we have for specified information being created? So like we have specified information in the world today. This book is full of it. The fact that there's donuts on the table, like we have cups that hold liquids, all of that is specified information. What makes that? Well, humans do. Agency does. Minds make those things. Like we don't see natural books forming on trees or trees or even living. So like we don't see them coming out of books. You know, if you find a tablet and there's words or things that look like words scribbled on it, you think a human from a long time ago, you know, probably carved that thing. You don't think it was natural, right? Like even our historians don't think that. Like you don't see an archaeologist saying, oh, look at this, you know, this carved tablet, it must have formed naturally. We just don't make those conclusions because it doesn't make sense.
UFAs, out of place artifacts or something like that, is like a thing in archaeology where they find something like, that shouldn't be here because our timeline says, like, in the Bronze Era, they weren't making microchips or whatever, and then they dig and they find something that shouldn't belong there, and it has a title because they're like, that shouldn't belong there. It throws everything off, but they don't just assume it just
happened naturally.
Right.
Yeah.
That's interesting.
Yeah. So like that, it's, you know, a design inference. Like you're inferring that something was designed because it has function, it has specified information to it. And life has that. And it's very complex. Like it's more complex than what we can do today, right? Like we create computers. Like my phone here is highly organized and for a specific purpose. And like you change anything about that, you just spill enough water on it in the right place and it's going to stop functioning because it's highly designed. Like the circuitry and the programming and all of that comes to play in it. And that's why DNA is so often attributed to being like code, because it functions just like code. It's alarming how much it's like code. And where did that come from? Like that doesn't just happen naturally. We have no explanatory, like there's no explanatory factor that explains where the information came from. Like the best thing that secular scientists have is chance over long periods of time. But we're talking numbers that just don't make sense. You know, so then, you know, you start saying, well, there must be an infinite number of universes, and you know, ours is like we're talking about this today because we're in the universe that it actually happened in. And if you have an infinite number of universes, everything's going to happen, like by its nature, and that just doesn't feel like a very good explanation to me. Like that just,
it's like a parent being like, but why? Because I said so. Don't ask any more questions. I'm like, okay.
Yeah.
So what was the response like from your reading and research of this over time? Like, what was this response when the Human Genome Project kickstarted and then became completed in a sense, where they sequenced the entire thing and they were like, whoa, right? Like there's a lot of information there. We've finally broken it down. It took this amount of time. What was the initial response of like the scientific community as a whole? I know it's a huge question and you're not an expert again, but was it like, everybody hold please, let's digest this, let's talk through it? Or was it like, of course we would expect to see this?
I don't think, I mean, I'm speculating here, but I think the past 50 years has been an explosion of like we're digging up the well and it's just getting deeper and deeper and deeper, and it's getting more and more complex. I feel like scientists kind of came into this thinking, you know, Francis Crick, when they discovered the helix and that there was information there, like, oh, this explains some things. We're figuring this out. We're on the cusp of understanding life.
Mhm.
And then they started getting into it and they're like,
Way more complex.
there's
Crap.
a lot going on here.
Gotcha.
You know, and like you back up even further, back in Darwin's day, they just thought it was they thought we were just made up of little balls of jelly.
Mhm.
And like those little balls of jelly are the most advanced nanomachines that we've ever seen and cannot replicate even with all of our technology today. And like, how do you explain that? They don't have explanations for that. But what they do is they basically come at the problem from this like constrained perspective, saying that we have to come up, there has to be a materialistic explanation. It exists, therefore there has to be an explanation of how it came to exist.
Are any of them actually offering chance as an answer? Or is that just a word that gets thrown out because they don't have anything else? Because I can't imagine the science, like, you wouldn't have made $3,000 that weekend if chance was a satisfactory answer to a medical point, right? Like, hey, let's just go toss these pills out to everybody because there's a chance that it might have this effect. It's like, no, we're going to like study and do these things and stuff. So I'm just wondering, like, we talk about chance and this stuff, and I'm wondering if in your reading, if any of these scientists have actually offered chance as a thing that is satisfactory as an explanation.
Yes and no. Hey, probably more no. I can't remember. There was a quote that I came across, and I can't remember it's been in this book or somewhere else, so I won't spend too much time looking for it. But it was something on the lines that, like, you can only have so much luck as a factor in your scientific theory. Like,
Because luck is the thing.
yeah, like you can only have so much chance in your theory. Because if you like for it to be valid, like you can have it starting out like here's a rough sketch on how it could have functioned, and then you start filling in the details. That's the goal of science. So like they're operating on this rough sketch approach and hoping that they can provide more detail to it. That they're gonna come up with some groundbreaking result. So like they're gonna come up with an experiment, something like the Miller-Urey thing, and like the right things in the right way, and then oh wow, it all starts coming together. Like they're looking for that sort of holy grail, and they're like, it must be there. We just need to spend more time and effort looking for it. It's kind of like there's another example that I read that I can't remember the exact details of, but like for whatever, I think so. Like ID, intelligent design theory, would say that like their biggest complaint is like it's impossible. Like there's nothing here that's saying that this is possible. Like that this is something that can actually just happen. And scientists are like, well, it had to because it exists. And they're like, well, there's other explanations. Like the explanation that best fits it is agency, is a mind, because we see that today in our own things that we make. But scientists are like, no, we need a naturalistic explanation because that's how science works. Science only works on that scale of things. Well, some science, like archaeology, is all about discovering agency and trying to figure out who the agent was that made it. That's what archaeology is. And so idea is like, hey, we should bring some of those concepts into some of these theories, and maybe that'll change how we do science. But yeah, to your point, like they're not comfortable with just saying, it's chance. That's a good enough explanation. But so like they're that bothers them, I would presume, that chance is not good enough. There's there are multiple quotes by Origin of Life, and evolutionary scientists are like, this doesn't make sense the way it is, but they're like, we'll figure it out. It's kind of they're optimistic, and that's good for the sake of moving science forward. But ID is challenging that and saying, there's a simpler explanation. Maybe we should investigate it. And then the scientific world's like, no, you're pseudoscience because that's not testable. it kind of is actually testable, or like it has implications, like it can change your approach to how you work on these things.
Is it also I kind of walked in late on the question, but I think I can understand where you were going with it. So obviously we're sitting here from a biblical Christian monotheistic perspective, right? Okay. So in the scientific world, we assume as Bible believing Christians that a secular science just doesn't want to admit that the God we believe in is the agent. In actuality, is secular science just is it an anti-Christian God thing, or is it simply just, do you know what I'm saying?
Yeah.
Because usually it comes down to secular science versus Christian pseudo science or whatever. But is that really the case? Or are we looking at it through a blurred lens of like them versus us, when in actuality it's like science just doesn't want to or cannot or will not admit that agency exists, period, no matter who you call it?
I don't think it necessarily has to be science. It's just that it's just the flesh.
Sure.
We don't want God.
Mm-hmm. But like, do you see what I'm asking when I say you never hear anybody saying like, well, we know that Allah didn't create this. We know that, I don't know any other religion and they're like God in creation. But like you go to the Native American,
Shiva.
Whatever, just it always comes down to Yahweh. It always comes down to biblical God, of them being like, it's not that, guys. And it's like, you never hear them saying anything else. But again, I'm like, I'm going to be biased in that because I'm going to pay more attention to a secular scientist that says, it's not the God of the gaps. It's not God.
Mm-hmm.
Or is it simply just agency? They don't really care who is saying it's our individual who is the agency. There's like no agency at all.
I think
because it's religion, no matter what religion that is.
When you said God of the gaps,
Yeah.
I think that's what science pushes back to on the most.
So it wouldn't matter who that God is, but
Well,
they always are like Christian.
I think there's a couple of things there. I think one, Christianity is the biggest Western religion, so it has the biggest target in a sense.
Because like you've got Europe and America that have the bigger colleges, that have the bigger labs.
Yeah.
Okay.
Yeah, and they have, it's more vocal opposition.
Okay.
I think there's also the Christian, careful how I say this, the creationism
Sure.
like aspect of Christianity that sometimes spins things in a way that seems ridiculous to scientists.
Sure.
And like they attack that.
Yeah.
You know, and like they often will lump creationism and intelligent design under the same thing.
Right.
And like we saw this at the Supreme Court level not that long ago, in the 90s or early 2000s, I can't remember.
The 90s.
Yeah, I think it was, the 90s, which Stephen Meyer actually testified in support of intelligent design. But the problem is like the message got so mixed into creationism and religion. And I'm not saying that there's anything wrong with creationism. I'm just saying that it comes from a different perspective. It comes from this is the Bible first, and we're going to explain things with that lens.
You're using the Bible as a
is.
scientific book and not a book of
Yeah,
all
no, you're
that.
good.
Yeah.
How do I pick that? Where do I get the recording? How do I get to that?
I'll
So,
send it out.
Yeah, you can also look for Design from Reason on Apple Podcasts or
Wherever you get
Spotify.
your podcast.
Wherever you get well, just Spotify and Apple.
Are there other places?
That's a good question.
YouTube is trying to get there. But where was I?
Creationism,
Right,
intelligent design, using the Bible as a book of science, which is not what it was intended for, but that's kind of where that comes out of.
Yeah, there's so like when you approach science and you're like, okay, there's multiple ways to approach it, right? Like, and looking at it as like Bible says the earth was created in 7 days. So I'm going to take that literally, and then I'm going to filter all the science I can through that perspective. That is an approach. Like, you can do that. That's an approach you can take. But but that approach means that it has consequences where it's like you're now saying that everything has the appearance of age. So like things that we observe that are old, starlight from a galaxy a million years away that we can see. I mean, that presumably took 1 million years to get here. Well, if you start narrowing that down, you're saying, oh, God started that light halfway here, or whatever it was, or like the rocks that have eroded over a long time. So, that God made it with appearance of age. Like, sure, you can say that. The problem is that's not you're looking at it from.
You're kind of doing what the secular world does,
Yes.
which is like, it probably happened over time. Don't worry about it. And everybody's like, wait a second.
You're coming in with, like, if your goal is to find the truth, you can't come in with presuppositions, or you have to limit them. You have to be like, okay, I need to look at this problem, look at the evidence, look at theology, look at science, look at current observations, and understand their limitations. Yeah. Like, one, the Bible wasn't written to be a science book. It was to tell a story about who Jesus Christ was and what our role on earth is. And, it's not trying to explain DNA, codons, and how our information works. It just isn't. So that's a limitation of the Bible. It's not a science textbook. You come in from science, and it's like, well, we have a physical limitation on what we can observe. We have eyes, we have ears, we have nose, we have mouths. We have tools that can help enhance those. But at the end of the day, we're limited to our perspective and the tools that we can make to observe the natural world that we're in. So we are limited there too. So like, you have to come at these things understanding that the limitations are there. So to answer your question, I think scientists in general look at explanations and they just cover them all with, that's a god of the gaps.
Yeah.
You're talking about Zeus being the reason for lightning.
Right.
And their main argument is, give us more time and we'll be able to figure out an explanation. Mm-hmm. And that's maybe not untrue. Like, we've seen that happen over and over again. Like, we can explain how lightning works now. Mm-hmm. We can explain earthquakes and why they happen with plate tectonics. Whereas, 200 years ago, those were acts of God.
Mm-hmm.
And,
or sickness
or plagues. Like, all of these things we have better explanations for. Right. It's like, oh, the Black Plague happened and that could have been a punishment, or it could have been that they were living in nasty environments with full of bacteria, or both. Exactly. Mm-hmm. So like, they're complicated things. And I think the reason why I'm drawn to intelligent design is it's just looking at the broad scope of evidences, mm-hmm. saying what makes sense here. Mm-hmm. And like, we will always bring our own biases in because we don't have omniscience. Like, we don't know everything. So like, we're going to hold certain things to a bigger impact than other things, where a scientist who is fully secular is going to say, I am coming at this with the presupposition that everything has a naturalistic explanation. Whereas many of us would come into the conversation saying, you know what, I believe there's a creator, there's a God, and I'm going to look at the science through that lens, and I'm going to interpret it. I'm going to look at it and figure out where things land. And like, sometimes there are hard things that you aren't really sure about, but you just keep working through it because we're not omniscient and no one is. Like, at the end of the day, we all have to make a best. We have to work through it and talk about it and think about it, which is why we're here this morning, is to work through these things. So like, I think I have to fight this bias, and I think most people do, is like trying to see science as the bad guy, or like mm-hmm. They just don't get it. Like, that might be true, and like, I think there is elements of that in in especially high academia where it's like just dogma and it's just like, if you like, you can lose your job if you don't come at these, from the evolution perspective, and you can get ridiculed.
Or you get a Wikipedia page that calls you a pseudoscientist.
Exactly.
Like overnight.
Exactly. Which doesn't make sense because like everyone I think is like most people are in that field are motivated by understanding what the truth is. And like, great. Like, let's understand where our presuppositions are coming from. And like, let's actually listen to arguments instead of just ruling them out. Like, the fact that, ideas just ruled off as a pseudoscience, I think is, doesn't make sense. It's not scientific. Mm-hmm. If you look at what science really is, it's like, oh, that's a theory that explains how this happened. Like, we know agency creates specified information. Mm-hmm. We see specified information in DNA. Why would we rule that out? Why would we rule that out? I think is the big question that I would challenge scientists with is like, what's so wrong with considering that as an option? I'm not even saying you have to believe that that's the way it happened. I'm saying just consider it as a potential option. Mm-hmm. Like what's that? That's science. Like look at all the ways this could have happened and try to explain it. And I would encourage scientists to still look at like other explanations. Try to go down the whole like let's try to make life from nothing path. See where we go. I'd be interested to see how far that can go. But it's not going very well right now. It's not going very fast, except in the direction of like we're just understanding more and more how complex things are, and honestly, like understanding how life works at that cellular level has come up with tons of medical technologies and advancements and crazy things that like we would have never been able to do, like like the CRISPR stuff and like
anti-rejection meds, so you can put a pig heart in a person and they don't immediately die. That's wild.
I mean all of that stuff is.
What's the CRISPR stuff?
CRISPR genes.
So CRISPR is a technology that lets you manipulate DNA basically and like
swap if that's possible to actually get in there and do anything with DNA and have it not be a complete disaster. They're able to do that?
Yeah, it's actually insane what they can do.
Maybe not the non-complete disaster yet, but
but like baby, if they do like some parents like to do genetic testing like when they're pregnant to know what they can plan and expect for with their child, like especially if you're a carrier of something, like if you're a carrier of a genetic defect.
So they can test for that.
They could test.
But they can't manipulate genes yet.
Well, so what they can do is they can turn them off. So like you can go in.
Really?
Yeah, you can go in and you can turn off genes that are in that sequence down there. Like, okay, if this gene continues working the way we know this disease or this mutation works, then this child will probably grow up and eventually develop this, or they will struggle with this. Now that's like if everything is wonderful and perfect and you don't go wild with it. And they are, like you can go in and say, we're going to turn that off. But then what a lot of people are saying CRISPR genes is scary is they're calling them designer babies, right? Like you go in for IVF or you go in for whatever they can figure out later on in the future, and you start with that little embryo that's like developing and splitting, and you're like, okay, I really want a blonde hair, blue-eyed baby. Mm-hmm. Turn this on, turn this off, and that's what you get. Mm-hmm. Or I want a kid that's going to be 6'5" because we really want a basketball star. Or I want a doctor, and so we turn off this gene that allows their brains to do this. That's the scary part of like what are you creating and designer people and designer babies. But
is that a continuation of what Hitler was trying to do?
Yeah, he just was trying to breed them in and out, like right. People here.
He was using
eugenics.
I was saying US did too.
Yeah, we 100% still are. Like, but like there is good in it because we do have mutations in DNA that causes children and people to develop diseases and terrible things that you look at, and eugenics would say like you just need to kill them because they don't have a great life, so don't even allow them to suffer, just kill them off ASAP. When in actuality it's like, okay, but if they don't know any different and they like they are a unique human being. Like that's a whole nother discussion. But CRISPR genes is turning that on and off. And you can use that for goodness. Like, what if your child is going to be blind or develop cataracts at age 5? Or you have some children that are born, I can't remember what it's called, but there are two terrible gene mutations that happen in children that you can detect for now, but we can't do anything with. And that's like where they're born and they are functioning and growing, but their body is like 80 years old. Like those rare kids where they look like an old individual and they only live for like 10 years and they die of like arthritis and things you would see a 90-year-old die from. You could turn that off in a baby or in an early embryo and give that child the ability to live a semi-normal life. There's also another mutation. If you ever go to the Mutter Museum, you should go because it's intense to see the Mutter Museum in Philadelphia. It's amazing. Look it up. M-U-T-T-E-R. It's so good. But there are 2 skeletons. There was one for a really long time, and now there's 2 because one woman passed away in the 90s, I believe, and she had this mutation, and she wanted her skeleton on display with this other skeleton so that someday someone could figure out a cure, and they're actually really, really close. They're really, really close. What it does is as you get older, all your soft tissue turns into bone. And so as you get older, as things break, like if your body, basically what happens is you turn into a living statue. Your soft tissue, muscles turn into bone to the point where eventually in their teenage years, a doctor will advise that the child find the most comfortable position to function in for as long as possible because you will eventually be locked in. Like your fingers won't bend. Anytime that there is damage to the body, that wound becomes bone even quicker. And then they die because they suffocate, their lungs start to get too hard, their hearts become too hard.
It's a terrible disease.
It's terrible. And you can see that skeleton on display right now by her. That was her will and testament. But basically, CRISPR genes would say, when we know that 2 parents are carriers and they have that baby, and we test that baby's DNA early on and say, holy cow, 100% they have that, that is how they will live. I can't imagine a parent being like, I'm just going to let that happen. You know what I mean? And so CRISPR genes could be amazing, could be incredible,
Well,
but
it's
can
actually
somebody do terrible things with it? Totally.
It's
Nuclear war.
Will they? Probably.
Yes.
Well, here's the I don't know, exciting / scary part is like there's a guy on YouTube. His channel is called the Thought Emporium, I think, and like he does stuff with CRISPR like in his garage. Like it's a very approachable technology. I mean, you have to know a lot. You have to be pretty smart, but like it's not something that like only $1 million labs can do. Right. This guy, he has a YouTube channel, and he's done things like modify yeast so that it creates spider silk. Yep. He takes like the protein that creates spider silk, and he mixed it into a yeast bacteria.
They did that with sheeps a long time ago.
Yeah, but like this guy did it in a garage.
Right, but like it's been happening since the 90s.
Yeah, CRISPR was
or glow in the dark nights.
Yeah. So yeah, you can kind of do these crazy things. Yeah. And people, there's a ethics national security risk even of like people.
The Chinese guy that did it with embryos
viruses and stuff. Yeah.
In the early 2000s has disappeared. Like he made the news and now he's gone.
So where does the government stand on that at this point?
No, I mean they're anti-human, like modifying, like
manipulating.
Yeah, like there's ethics that try to control it, but
they were talking about it on World News a show ago. They had a guy on who I forget the terms he used now, but there's there are heritable and non-heritable ways that it's done. Yeah. And so the problem with the Chinese guy is that he made a change to 2 babies. Mm-hmm. One of them lived, the other one didn't. And the changes that he made were heritable. I'm not using the right word, but they were passed on.
Yeah. And the one that died got which ones?
Oh, I don't remember exactly. I have to go back and listen to.
Oh, but both babies had the change that was
something like that, and the changes that were made will probably lead to like a lot of bad things to it's not just this. It's not this simple like, hey, we're gonna change this with like everything cascades.
Yeah.
So it's not just it's cool stuff in its own way, and there are the things you can do, but it's not so cut and dry as like, oh, we're just going to simply flip this or flip that.
Yep.
It's like it's all tied together.
So like the COVID vaccines, they were messenger RNA vaccines.
That's what I've heard.
Yep. mRNA.
Yeah.
mRNA. So like the COVID vaccines, and I'm not an expert in this, so take this with a grain of salt or fact check me. Those vaccines were developed and basically injected you with messenger RNA that encoded for the antibodies for COVID.
It's like
So-
chickenpox, the chickenpox vaccine, MRSA stuff, or not MRSA.
So the mRNA vaccines are fundamentally different than other vaccines because the other vaccines, they inject you with like a wounded or dead virus. So your body learns how to make the antibody without being at risk of getting the full-fledged thing.
Right.
mRNA, those vaccines skip that step and just give you the pure information that your body needs to make the antibodies. And that work was being done. Like mRNA vaccines have been an area of research for the past 20 years. But then COVID hit, and like it was like.
Is that the first time they used it?
I think so. I don't know if it's the first time they used it, but it was the first time it was widely used for sure.
Yeah, and quick. Like, it's hard to. Yeah.
They got a lot of funding really quick.
Yes.
And they were able to accelerate things and get it functional. Like these, there's a lot of medical advancements that are coming as a result of this, but with any technology there's a dark side to it,
and risks and just side effects,
unknowns.
Totally.
Is
it polio? Was polio mRNA? Polio vaccines?
I don't think so. No, I don't think so.
Google says COVID was the first one.
Was it
approved for human use?
Okay.
Yeah.
So who knows the other ones that are like?
Yeah, I thought that was the case. That it was a pretty big deal.
Was it ready?
Define ready.
So I watched.
There's a question.
Yep.
Probably, not. They definitely got a lot of funding to move it quickly.
Yeah.
They.
It would have been so great if that had been done without political. Like, could it have been better? Could it have? Who knows? But like the fact that it went straight into politics, I'm like, oh my Lord, what are you doing?
Yeah, it made it very complicated.
Absolutely. Like, holy.
I listened to an interview from one of the guys who worked in the lab that had been studying mRNA vaccines for the past 20 years. And he's like, this is a technology that wasn't just like overnight to make the COVID vaccine. Like, we've been working on this a long time. But like when the pandemic hit, like obviously we got a lot more funding, and then we also were able to it was pretty much ready, and then like this was like a forced hand sort of thing. It was like, okay, we can actually make this, we can do this, but like the long-term trials obviously couldn't have been done. It's not like they could have like gave someone a COVID vaccine and then watched them for 20 years. It just wasn't possible.
They're like, here you go.
That's what you were actually testing there. You probably got some weird DNA information now. It's fascinating, but like the effects of these things are really like viruses can affect your DNA through these same sort of factors.
Like polio.
Yeah,
those kids can walk. Got polio. You're crippled. Big things.
Yeah. Any other thoughts or questions before we wrap up? We're almost at time.
I completely understand this. No questions, no money at all.
Yeah, it's a complex topic, and it's very deep. Like, I mean, people go to school for this and become microbiologists, and we're just scratching the surface of it.